So hi guys. My name is Owen, Coach Owen, and I'm leading today's first session for the TK math team. Yeah, super happy to see all of you guys. There'll be another slide later with a bit more about the introduction. Let's see. So yeah, the first slide here is just about showing your faces on Zoom. I think most of you guys have your cameras on already, so we're good there. But let's move on. Yeah, so these Wednesday sessions with Miss Dawn, we're gonna be going over the book for the Rising Math Olympian. You should have received a book or a packet of some sort with the material we're gonna talk about. And this book basically goes over a lot of top math concepts that are gonna be really, really useful when you do math competitions, such as algebra, geometry, number theory, counting, and a lot more to come. And today in this first session, here's our agenda. So we're gonna have a super short section on meeting the coaches. So there'll be me and Coach Woma, who might join us later. We're gonna have a little game. We're gonna have a Kahoot quiz to do some vocab right off the bat. And then we're gonna go over some math vocabulary, the order of operations, some counting techniques, and we'll have some review rounds and team rounds at the end, which are just like some questions we're all gonna do together. That makes sense? Yeah. So hey guys, my name is Owen. I'm one of the coaches that's gonna be helping you guys during this program. I work in AR/VR, which is augmented reality and virtual reality, doing a lot of super fancy computer vision stuff for Oculus, which is it's this like VR headset you guys might have heard about before. You can play games on it and talk to other people with like avatars and messages and stuff. When I was your age, I was starting to do the AMC competitions. So has anybody heard of the AMC? Yeah, I see a couple hands. Yeah. Um, yeah, it's basically stands for the American Math Competition, I think. And there's like different levels for 8th graders, 10th graders, and 12th graders, but you can do them at any age. So yeah, I did a lot of math competitions when I was in middle school and high school too. And some of my favorite things to do in my free time are I love playing on the Switch, so I'm really into Super Smash Bros. Ultimate and Zelda Breath of the Wild. Those are my two favorite games. Cool. So now we're gonna start off this session with Kahoot. I'm gonna share my screen and go over to the Kahoot page right over here. And you should see the purple page for Kahoots and a pin come up shortly. You can, yep. All right, what did we get? Positive numbers, yes. Cool. Let's move on to the next question. And don't worry about getting this right or anything. This is just kind of like a fun intro to what we're going to talk about all of these later. Question 2 out of 7. So, on the other hand, what are numbers less than 0 called? Put your answers in now. Sweet. Okay. Negative numbers, that's right. Okay, next question. 0 is, well, this one's tricky. In your guys' you guys' answers, and we'll see on the next page. Correct. It's neither negative nor positive, because the definition of zero is actually really crucial to both of those terms, which we'll see later. Okay. What are natural numbers? You guys might have heard of this before. Yeah. A lot of the math vocabulary we're going over today are like different ways of classifying numbers. Yep, so natural numbers are positive numbers, but without fractions or decimals. Whole numbers is a really good guess. We're going to talk about the tiny difference between them later. Okay, so which one of the following numbers is a whole number? Okay. What did people put? We have, ooh, this one looks like it was a tough one. Yeah, 0 will be a whole number. Okay. Here are the scores, and I think this is the last, nope, second to last. Question 6. All integers are also rational numbers. Is that true or false? It's true. Yes. Okay, let's put a bookmark in that one. We're going to talk about that one too when we get to rational numbers. Rational numbers are super cool. And the last question. So if you can combine all rational numbers and all irrational numbers, what group do you get? All rational and irrational. Give this your best shot. You may or may not have heard of all of these terms before. That's okay. Yep, so if you combine all the rational and irrational numbers, we call that set of numbers the real numbers. So a lot of words flying around, a lot of different like groups of numbers that are for our math vocabulary, and we're going to talk about what each one is. Good job, guys. I'm really proud of you all for going through this quiz. Okay. I'm going to stop. Okay. I switched back to the slides. Can you guys all see the Google slides? All right, chill. Yeah, so kind of like the Kahoots quiz was talking, kind of hinted at, today we're talking about some math vocab and order of operations and stuff in that realm. So first off, for our math vocab, a lot of this stuff I think a lot of you guys already heard about. Some of it you will have not heard about, and we're gonna focus on that. But if you already know what these are, we can just treat it as review. Yeah, so there's a lot of numbers, and to talk about it, mathematicians have like different vocabulary words to talk about some numbers and not others. And these are different ways to group numbers, and they'll prove to be super useful. So positive numbers are the definition of a positive number is a number that is greater than 0. So yeah, all these numbers here, such as like 1 through 9, and any number that's bigger than 0 is a positive number. So here are some examples of positive numbers. It could be decimals or fractions, or they can be numbers that land on the dot, like 120 or 4 or 36. And that's how the number line would look if I were to highlight all of the positive numbers. So it's everything to the right of 0. So negative numbers are any number that is less than 0. Can you guys send in the chat like which one of the numbers, the little cartoon numbers on the bottom, are not negative numbers? Yep. So I see a lot of people sent 0 and 1, and that's right. Those two are not negative. Yeah, you can also kind of tell because they don't have a negative sign in front of them, which is kind of a workaround here, but yeah, they're less than 0. And that's why they're negative. So if I were to highlight the negative numbers on a number line, it would look kind of like this, the entire yellow portion. Everything that is to the left of 0. And yeah, those are negative numbers because they're less than 0. 0, however, by itself, if you think about 0, why is it neither negative nor positive? Can someone explain in chat? Just in like English words. Yeah, so it's kind of like a technicality. It's kind of got caught in between the two rules because I just said that any positive number is something that is greater than 0. And 0 is not greater than 0. 0 is exactly 0. And a negative number is a number that is less than 0, right? Such as -1, -2. But 0 itself is also not less than 0. It's equal to exactly 0. So it kind of falls in the crack between the two definitions. And that's why we treat it as neither negative nor positive. So if you ever see that on like a competition or a question that says like, I don't know, like what are all the positive numbers that satisfy this rule? Remember not to include 0 because it doesn't count as one of those. Yep, and this is number line kind of illustrates that because it doesn't fall under either definition. Yeah, I'm reading your guys' answers in the chat. That's super good. You're all right. Yep. Okay, those two were some of the ones you might have heard before. So this next one, natural numbers. Who has heard of natural numbers before today? By show of hands. Okay, I see a couple hands. Yeah. So another word for natural numbers is counting numbers. I think it's more like a everyday kind of word, but mathematicians use the fancy like hollow n to denote the set of numbers that are the natural numbers, and these are all the positive numbers that don't include fractions and decimals. So I like to say they have to land on the dot, which means like it can't be like half or like 1/3 or anything in between, basically. So which one of these cartoon numbers below is not a natural number? Yep, 0 is not the natural number because, again, like we just talked about, it's not positive. And all natural numbers are positive numbers. Yeah, so all of your typical counting numbers from 1 onwards is a natural number. 1, 2, 3, 4, 5, and so on. Whole numbers. This was something that came up in the quiz. And the definition of a whole number is anything, or a whole number is 0 and all of your natural numbers. So it's super similar to natural numbers, but when we talk about whole numbers, we're also including 0 as part of it. So you can see in the example below. So 0, 1, 2, 3, 4, and so on and so forth. Those are your whole numbers. Negative numbers don't count. And fractions and decimals also don't count. Is this making sense to everybody so far? Okay. Cool. And we're going to talk about an even bigger group of numbers now. We're going to talk about the integers. So integers we mathematicians refer to them with that fancy z. And the reason they use z is because I actually don't know why. I was about to give a reason because I think like when in Greek they had in German when they first came up with the system, the word Zala means like digit. So they used a fancy Z back then, and it's just stuck ever since. Yeah, so integers or that Z is all the numbers. It is zero and all positive and negative numbers. So these are all numbers that like fall on the dots on your number line. So -1, +1, all of those counting numbers as well as their negative counterparts count. And we're not including fractions or decimals. Okay. Yeah, these are some examples like -5, -4, -3, -2, -1, 0, 1, 2, 3, and so on. And this is how they look like on the number line. Those blue highlighted regions would be like infinitely small because it's just one number, but that's how it would look. Rational numbers are where things get a little fun because the definition is more complicated. A rational number, or who has heard of rational numbers before? Okay, a good number of people. Yeah. Okay, so rational numbers that are all the numbers that can be written as a fraction of two integers. Oh, yeah?
Oh, and I want to ask them, can you send us in the chat of what's a number that's not rational then? Is there any number that can't be represented as a fraction? If you can think of one, tell us in the chat. Okay, I see some people are saying pi. Good. There are other numbers too. Okay. Cool. Sorry, Owen. I just want to ask that question.
Yeah. So, Alicia, I would pose a challenge problem here. Can you write that decimal you just sent as a fraction? How would you do that? It looks like a really long decimal, right? I can't even how would you write that as a fraction? So one way to like write a decimal as a fraction, because when we talk about decimals, they're all like, for example, if I say like 0.9, that's 9/10. Oh, someone raised their hand?
Yeah, are like irrational numbers like square roots? Would that count?
Yeah, some square roots are irrational numbers. Do you know an example that you want to share with us?
The square root of 2.
Yes, the square root of 2 is an irrational number. So no matter how hard you try, there are no two integers that ever you can put as a fraction to ever equal the square root of 2 exactly. And Alicia, yes. Yep, that is how you write it. It's because so decimals are easy because you can always put it over like 1 followed by a bunch of zeros, as many zeros as you need until like your decimal is like shifted the right way. Yeah, so they're rational numbers. Yep. What does the number line look like for rational numbers? So I gave this definition that isn't as translatable, right? Because when I say positive numbers, I say like, oh, it's greater than 0, and it's easy to just like sweep everything to the right of 0 and visualize what it means to be a positive number. We're not going to be able to draw it exactly, but do you guys have any ideas on what, if I were to color all of the rational numbers on a number line, what it might look like? Again, these are every number, any number, as long as it can be written as a fraction, you can, it qualifies. It falls into the rational numbers category. I'll give Isabel, is your answer for the question I asked? Or did you send it earlier? Yeah, so you said it's a line. Can you explain what you mean by that? Yeah, It's a little quiet, but I can hear you.
Like, I mean, technically a line doesn't have any thickness, but if you put like every single dot on like every single infinite point, it will make like infinitely many points. I guess I would like to make a line.
Yeah. So yeah, there are infinitely many rational numbers, right? Because there's infinitely many numbers, and you can just like keep making more. Yeah, and it would look like it takes up almost all of the number line. You see it here. Yeah, so most of the fractions and decimals and in between numbers, as well as like the integers themselves, because you can always write everything as a fraction over 1, right? So those would all be rational numbers, because like any decimal you can think of would fall on the rational numbers. And this number line actually should include these points. I didn't highlight these points, unfortunately, but you can imagine it's like pretty dense. It covers the entire number line, but I would like to add an asterisk to that. There are also infinitely many irrational numbers, which is kind of mind-boggling, right? Because you have infinitely many rational numbers that fall in this line in every which place. You also have infinitely many irrational numbers. And just a cool fun fact that maybe we don't have to go in depth right now. All these guys are interested. There's actually more irrational numbers than rational numbers. And the irrational numbers are way, way, way bigger than the number of rational numbers out there, even though both are infinite. It's like a bigger infinity, which, yeah, I don't know. It might be confusing, but like it's really cool why that works. But if we're talking about rational numbers, I think what the important takeaway here is like anything you can write as a fraction counts as a rational number, and that satisfies a lot of numbers. Oh, and just for fun, here's something I'd like us to think about. So, having talked about rational numbers this whole time, you notice if I were to, if I were to just write out some rational numbers like here, like 1/5 is 0.2, right? 2/7 is this really long decimal expansion. 3/8 is 0.375, and so on and so forth, right? Can you guys give some examples of rational numbers in the chat? Pick your favorite one. Pick one you think is like really unique. Yeah, those are all good answers. And the numerator can also be larger than the denominator. I didn't give any examples here, but I can do, for example, like I think someone said 10/3. That's also a rational number. That's like 3 1/3. And my question here is this: if I think of all the rational numbers in the world, or I just start listing some examples, right? You notice some of these decimal expansions terminate. So if I do 1/5, it's 0.2, and then it stops. If I try some other rational numbers like 2/7, and I try to write it as a decimal, it doesn't stop. That goes on forever. And I think something cool to think about is like, for all the numbers that do stop and all the numbers that don't stop, what is the difference between their denominator, q, in this fraction that you can write as p, some variable p, some number p, over another number, some number q? You guys can try, I'll give you guys a minute just to like think about it. You can write down some examples or use your calculator or phone to try some out. You can just try like 1/5, 1/6, 1/7, 1/8, for example, and see if you notice something special about the denominator q in all of these fractions.
So yeah, you can get a calculator out to help you with this experiment, investigation.
And maybe next week, if you guys figure out the pattern, and if you can figure out why that pattern is, it'll be awesome. We'll visit this again next week. We'll move on to some other stuff, but yeah. And also, like, throughout this lesson, if you guys ever have like a cool idea you want to share, just pop it in the chat. A cool idea about this challenge problem. Okay. Yep, so to wrap up our discussion on math vocabulary, this is kind of like a Venn diagram, except all the circles are inside one another, about how all of the things we learned fit together. So this blue circle is the whole numbers, 1, 2, 3, 4, 5, and so on. Wait. No. The blue circle is the natural numbers, right? And then when you add 0 is the whole numbers. I have to check the slide. But yeah, those are those two sets of numbers in the blue and the red. The green circle here is z, the set of integers, and this includes all of our negative numbers as well. And the set of rational numbers q includes all these decimals and fractions and everything you can write as a fraction. To zoom out a little bit more, the set, you don't have to learn, this is not as important, but there's also a set of numbers called the irrational numbers. These are special numbers that can never be written. You will never find a fraction representation for those numbers. And every number you can think of falls under this set R, which we call the real numbers. Right, so any traditional number you can do addition, subtraction, multiplication, division that you've learned up till now is a real number. And I've just told you what R stands for, is the real numbers. Cool. Yeah. So now that we talked about math vocab, let's go over order of operations. Have you guys heard about PEMDAS, this acronym before? I see nods and thumbs up. Yeah. Okay, so this is the order of operations. So when you have like a really long arithmetic expression, you gotta do some things before others. You can't do all of it at once. And PEMDAS is a good way to remember what to do first. So you do anything in parentheses always takes priority. It's an explicit way to indicate you want something executed first. And then you can do exponents. Then you do multiplication or division. And then you do addition or subtraction. Multiplication and division are interchangeable. It doesn't matter which one you do first. And the same goes for addition, subtraction. So here are some examples. Send your answers to these 3 examples in the chat.
And we encourage you to send them all at one time. So do all 3 problems on your paper first and try to send it privately to Coach Owen. So you see under co-host, right? He should be like the first, second person after everyone. Just send it privately to him.
You guys can wait. Until you get all 3 answers. Type them all out with commas or something, and then send it to me. Cool. I see all really good answers. Keep them coming. Okay. I see a lot of people are sending me stuff. Now, let's do one more minute. Yeah. Okay. Yeah, we're gonna go over all of these now, so we can see how order of operations works with each of these expressions. So example, it's okay if oh, sorry, my chat did a thing. It's okay whether or not you finished. We're just gonna go over it so we can see how order of operations works. Yeah, so for this first example, we have 2 times, open parentheses, 7 minus 3, close parentheses, plus 6 divided by 2. The first thing we have to do is solve for stuff in the parentheses. So we get 7 minus 3, and that's 4. So we resolve that first. And the next thing we do is exponents. Are there any exponents in this expression? Yeah, there's no exponents here. So we don't do anything. We move on. Next thing is multiplication and division. So where do we have multiplication and division here? We have the first two numbers, 2 times 4 is a multiplication. And the last two numbers, 6 divided by 2, is division. So we're gonna do each of those. And you can see on line 3, 2 times 4 is 8. And then we do 8 plus 6 divided by 2, and 6 divided by 2 is 3. Right, so then we do 8 plus 3, and that gives us 11. Good job, everyone. Okay, here's example 2. So this one is 17 minus 4, 17 minus 5, in parentheses. And then we're going to do divided by 4 times 3 plus 5. So again, we're going to do the parentheses first. And we do 17 minus 5, which is 12. And then we do exponents. Again, no exponents in this expression, so we move on to multiplication and division. So we do 12 divided by, we just go left to right because it doesn't matter which order we do it as long as they're all next to each other in a big like bunch. So we can do 12 divided by 4 first, and that 12 divided by 4 gives us 3. And the next number is 3 again, so 3 times 3 is 9. And then we do 9 plus 5, which is 14. So the answer to the example 2 is 14. Does anybody have questions so far? People are following along, right? Okay, sweet. Example 3. This one does have some exponents, so we finally get to use that step. We do parentheses first. Oh, but inside the parentheses, there's another exponent. So how do we deal with that? First, we're gonna do the exponents. So whenever you see parentheses, you treat everything inside as like its own separate problem. So before we move on to the rest of the expression, we're just going to do what's inside the parentheses. And then we can do this whole process again, right? When you have 3 cubed, 3 to the power of 3 minus 25, we got to do the 3 to the power of 3 first. So that gives, if you do that, it gives us 27, because it's 3 times 3 times 3. And then we can do 27 minus 25, which is 2. And that's everything in the parentheses, right? So then we move on to exponents. You see the inside of the parentheses 2. So 2 squared is 4. And then you do 3 times 4 first, because that's multiplication, and it beats out addition. 3 times 4 is 12 on line 3. It turns into 12, and then we get 5 plus 12, which gives us 17. So if you follow PEMDAS, if you follow this order of operations here, that'll help you get the right answer doing these math equations. Does that make sense to everyone? Cool. Okay, now we're going to talk about counting strategies. This might sound easy because you're kind of like, you know how to count, right? Like, you just count numbers going up or down. But these kind of strategies are for like when you need to count really, really big intervals, and you can't always do it on like in your head or on your fingers or like on paper. So to start off with, how many numbers are between 10 and 20? Can you guys send it to me personally in the chat? Yeah, I see a couple different answers. I see some people saying 10 and some people saying 9. Does anyone want to talk about their answer or why this is confusing? Yeah, you guys can unmute yourselves and talk. I don't know how to pick on somebody. Mr. Wan?
I did 20 minus 10 minus 1 because since it's between, you just subtract it and then you minus 1 again.
Okay.
So I just counted.
Yeah, so one of you guys asked me a question, does 10 or 20 count? And here's the answer. So when you're counting the numbers, this is why it's confusing, right? Because when you're counting the number of integers, between two other numbers, does like 10 count or does 20 count? Because if 10 and 20 counts, that changes your answer, right? Or if like you're not including 10 or 20, that gives you a count that's completely different. So we distinguish these two situations by saying we're counting the numbers inclusive, which means you include A and B, the edges of your interval, or you can say it's exclusive or not inclusive. It means A and B are not they're not included in the count. So if I were to say the number of integers, if I were to say like, then I want you to count the number of integers between 10 and 20 inclusive, then the answer would be, it would actually be 11, because you would go 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and then 20. So you'd have 11 numbers. If I were to say it's exclusive, then you don't count 10 or 20, you only count what's in the middle. So you go from 11 all the way to 19, and that gives you 9 numbers. And you can use these two terms, inclusive and exclusive, for either end. So you could say like inclusive of your starting number or exclusive of your final number. An easy way to kind of like, so if you don't want to like count on your fingers or on a piece of paper or like in your head, because sometimes they'll ask you to count like all the numbers between like 1,337 and like 42,600 or something, right? You can really quickly get the count by using this formula. So inclusive, you want to subtract the smaller number from the bigger number and then add 1. If it's exclusive, you want to subtract the smaller number from the bigger number, same thing, and then subtract 1. And I drew this here on the number line to show you guys why. When you subtract A from B, what you're actually getting, the answer you get from that represents the number of dots after the red dot A, up until the blue dot B. Including B, but not including A, right? Because if I do you have to do 5 minus 3, it's 2, which is only 4 and 5. That's why you need to add 1 when it's inclusive. That way you can capture the red dot as well. And when you're trying to, here we go. And when you're trying to do stuff exclusive, you don't want the red dot or the blue dot. You just do B minus A again, but then you subtract 1 to chop off what the blue dot would have been. Is that clear? Okay, I see some thumbs ups. Let's move on to some examples. Or this is not a new example. So yeah, okay, it is. How many integers are between 1 and 10 inclusive? You can use the formula. So it's 10 minus 1, which is 9. Then you add 1. So it goes back, it's 10. So yeah, which should match intuitively what you get from counting. If I go, how many integers are between 1 and 10 exclusive? You want to use, you want to use the other formula where it's B minus A. And then, subtract 1, so it's 8. Cool. So here are some other examples. And you guys can work these out in breakout room afterwards. I'm just going to scan through them. So Jeremy read from page 24 to page 158, inclusive. And the question is, how many pages did he read? And if you use the formula, you get 135 pages. You subtract the 2 and you add 1. Zachary counted all the integers between -45 and 233. How many integers did he count? And you can use the formula again, but exclusive, right? So you're minusing 1. You do B minus A minus 1. And if you plug everything in, again, you guys can work this out on your own or in breakout. The answer is 277. Okay, let's do some review and team rounds.
Wait, Coach Owen though. But we end at 4:30. Should we just have them go in the breakout rooms now and work on those problems?
Yeah, I think that's a good idea.
Okay.
Do you guys have access to these slides? Is that something you guys want to look at?
I don't think they need to do the slides, right? They just what page is that? Kaden, look at the page number. What does it say at the bottom? The problems.
Is it these?
Oh, okay, yeah. I guess focus on those. How can they remember this? Write it down on your piece of paper that we're just gonna do these ones, 7, 8, 14. And then once you've written those down, or just circle them on your book, that those are the ones to focus on, then you can just join your breakout room.
Are we doing them together?
You can work on it in it's up to your group. You can work on it individually, but then come together. Yeah. Hi, Akshara. I want you to circle in your book the problems right here, 7, 8, 14, 15. And then you can join your breakout room.